Well, let's begin chapter 2, which is energy, and explicitly the first law of thermodynamics, which is another way of stating it, the conservation of energy. Areas that we want to focus on related to energy are going to involve internal energy as well as kinetic and potential energy, which you've had quite a bit of that already in your physics courses. And then we want to deal with our work and power, power being the work per unit time, the amount of heat that we are exchanging, and the various modes that we can go ahead and make that type of transfer, as well as what do we get when we have a refrigeration and a heat pump cycle, in addition to that of the power cycle, such as how do we create a 1,000-megawatt power plant. This first part of chapter 2 will really deal with a closed system. So with a closed system, we can still have a great deal of energy exchange, but the closed system does not exchange mass. But we should still be able to evaluate the performance that we have. Now, that performance for power systems can be exchanged or expressed as efficiencies, and for refrigeration systems and heat pumps, they're usually referred to as coefficients of performance. But in all situations, what they do is they state how much energy did we exchange relative to how much energy we could have theoretically exchanged. Energy by itself is an extensive property. That is, it could be a joule or a kilojoule of energy, or equivalently in the British system, a BTU, a British thermal unit. That is our extensive property. Frequently, we deal with energy as an intensive property, which means per unit mass. Therefore, our kilojoule per kilogram would be an intensive property. Similarly, our BTU per pound mass would be an intensive property. I had stated that a closed system does not exchange mass. Therefore, the only way that the energy can be exchanged is through heat and work. Fundamental to all of our things is that energy is conserved. In fact, that is the first law of thermodynamics. The closed system energy balance is really saying that the change in the amount of energy within the system, once again, that system is something that you define, has to be balanced by the net amount of energy that has crossed the boundary. Now, it can cross that boundary by having work performed, or it could cross the boundary by having heat go either into or out of the system. That's our only mechanism for energy exchange between the system and the surroundings. We describe energy in three terms: our kinetic energy, our potential energy, and our internal energy. You will find, even though we're starting out dealing with kinetic energies and potential energies, it is really the amount of internal energy that really holds the majority of all of the power and utility of using thermodynamics to make refrigerators work, heat pumps work, and power plants work. When we deal with the change of kinetic energy, what we're really talking about is the change in the motion of that system. And the primary ingredient of that is the mass of the system, as well, which does not change, and the velocity, which could change. Our mathematical formulation for the kinetic energy change, that is, the kinetic energy at state 2 less the kinetic energy at state 1. This is the change in kinetic energy as we go from state 1 to state 2. It is equal to the mass times the velocity squared at the final state relative to the initial state. This is our formulation for kinetic energy. Your physics courses have certainly addressed kinetic energy, and they have also addressed potential energy. Potential energy is the change in the elevation relative to the gravitational field that you have for your system. And that change in potential energy is the potential energy at state 2, which is the mass times the gravitational field times its elevation, less the potential energy at state 1, which again is the mass times the gravitational field and its elevation at state 1. For a system, the mass does not change. Internal energy is a major component in doing thermodynamic analysis. It is associated with the actual makeup of the system, and it could include chemical compositions. Unlike kinetic energy or potential energy, where we can actually take a stopwatch and measure what the velocity is, or that we could take a length scale and measure what the elevation changes are. To actually measure the amount of internal energy is really quite difficult. And therefore, what we always refer to are essentially tables of data that have been compiled for virtually all working fluid components that we might need to address. Internal energy, kinetic energy, and potential energy can all be explicit external, internal energy, like kinetic energy and gravitational energy, can all be extensive properties, and they could be intensive properties. And the only difference between the extensive property and the intensive property is that one is that quantity of energy per unit mass. To summarize, we can state that the change in energy from one state to another state is the change in energy, the E2 minus E1. It's going to be equal to the internal energy change from state 2 to state 1, the change in the kinetic energy from state 2 to state 1, and the change in potential energy from state 2 to state 1. What we have to remember is that the energy will not be destroyed. It is conserved. Frequently, we just deal with it as delta E is equal to delta U plus delta kinetic energy plus the change delta potential energy. Energy can be transferred only through work and heat across a closed system. Once again, in a closed system, you have no mass exchange. That's an important distinction. You have dealt with work in your physics courses, for mechanics, and you know that you can get work by having shaft work, such as a propeller turning. You know that you can have heat going across a boundary as you have a gas flame try to heat up a tea kettle. If your system is the water within the tea kettle, you are adding heat to it, but you're not changing the mass of it. These forms of energy exchange can certainly be dealt with schematically. If you do apply a force and you compress a spring, that does require work. How much work is it? Well, it's somewhat the force that you are applying times the compression of the spring is your quantity of work. Similarly, if you do have a paddle wheel that is rotating around and around, it will be taking the work to have that paddle turn, and it's going to convert it into work within this system, which will add energy into it. That is, it will heat it up. For our thermodynamic sets of equations, we use the term W to denote work, and that is the work that is transferred. Since most engineering applications are concerned with internal combustion engines, power generation, the idea of work as positive is when the system actually does work for you. So when we put high pressure steam through a turbine, that turbine spins a shaft which runs an electric generator to create the electricity. It generates work, and that work we view as positive. If we have to apply work to a system, such as we have to plug the refrigerator into the wall in order to run the compressor, then that work is negative because it is done on the system. The exchange of energy by heat can only occur in one direction. Heat is transferred in the direction of decreasing temperature. It violates, and we'll talk about it later, the second law of thermodynamics to add heat from a cold source into a hot source. So if I have this gas heated up through this hot plate, the heat will transfer from this hot plate into the gas, going from a hot temperature into a colder temperature. Now that heat might also go from a warm temperature into a cooler temperature out to the surrounding environment, if you think about this being your coffee cup. Heat is denoted by the symbol Q. An uppercase Q implies that it is an extensive property. It is a certain quantity of heat in BTUs or in kilojoules, perhaps. A lowercase q implies that it is a intensive property, which is that amount of energy, BTUs or joules, per unit mass. And if heat is added to the system, the definition is that that would be positive. If heat is taken away from the system, the definition of it is that is negative. These are just pure definitions. It has been defined that heat added to a system is positive and heat removed from a system is negative. Another thermodynamic term is called adiabatic. Adiabatic implies that there is no heat transfer between the system and the surrounding. The first law of thermodynamics for the closed system can be stated that here we have the change in the amount of energy contained within a system. That could be the change in the internal energy of the system, the change of its kinetic energy, the change of its potential energy. It is going to be balanced by the amount of heat transferred in due to heat, and therefore that would have a positive Q, as well as the amount of work that is done by the system. So if there is no exchange of heat with the system and there is no work performed by or performed on the system, then the change in our energy of that system would be the same. The only way it can change is through a heat exchange and a W. Frequently, we want to deal with power. So our change of energy with respect to time is the change of the, is the quantity of heat that is exchanged per unit time and the quantity of work that is exchanged per unit time. And work per unit time is the power.